All right, happy Tuesday, back from break. Everyone relaxed. We are finishing applications of integration today. That's the goal.
That being to be this could be another test.
We look at center of mass. Okay. Conceptually, center of mass is fairly simple. Right. Let's say you have, we'll go with that. You have a weight, or you have a scale, but you can move the point at which the scale balances. And so you put masses on either side. The center of mass would be the point where you need to put the fulcrum so that it stays perfectly balanced. We can treat objects as point mass systems, which is nice. In terms of reality, if you take a look at our solar system, you were taught that the Earth orbits the sun, and specifically that everything in our solar system orbits the sun. That is incorrect. What they orbit is the center of mass of the solar system. Now, the center of mass happens to lie within the radius of the sun, which is why it looks like everything's orbiting the sun. But if you actually look closely enough, you'll see our sun wobbles because it's also trying to orbit the center of mass. A really good example of this in our solar system is the Pluto-Charon system. Right? Charon is the moon of Pluto, but if you actually look, because they're about the same size, same mass, they're actually orbiting each other. Not like our moon, where it looks like it orbits the Earth because the center of mass between Earth and the moon is within the Earth's radius. This is also observable if you observe a binary star system. The two stars wind up orbiting each other. Right, so they orbit the center of mass. Let's look at a two-dimensional object called, we'll say, thin metal plate called a lamina. The idea is the same. The center of mass of the lamina is the point at which you'd have to put a fulcrum to perfectly balance it. You have several options for lamina, right? You can have a lamina whose density is constant throughout the entire lamina. So in that case, it would all be made of the same metal. You can also have variable density, right? So you can have a lamina made out of different materials. Each material has its own density. However, we're going to make the assumption that the density is a function strictly of either the horizontal variable or the vertical variable, not both. That would require Calc 3. So we are still making a simplifying assumption here. We're also not going to look at three-dimensional objects. That also is going to require Calc 3 to find the center of mass. Find center of mass, linear wire covering the interval -3 to +3, and has a density of 1 plus 3x squared. What we're going to do is assume that this wire is thin enough that we can treat it as just one-dimensional. If the density happens to be constant, the center of mass should be relatively simple to find. It would just be 0. Actually, it's going to wind up being 0 anyway, which is kind of nice.
And you see that right now because it's an even function.
Well, I haven't gone over the formula for center of mass.
Well, yeah,
But yes,
you know,
it's
an
going
even
to wind
function.
up
You know that
because of the
it's
formula.
balance, not because of, I mean, you could solve it with the formula, but you could also just imagine it'd be symmetrical.
Well, define even function when you're talking about like dense. Like if I just give you a wire,
Well, this function, p of x.
and
is
but
even-
I don't give you the density function,
Well, we did get the density.
right? So that's why the formula is important. Because what does even density mean physically?
Well, it means that if you choose any point like x from your center in one direction and the other direction, there will be the same density in both of those places.
That mean the density is even. I agree the density function would be even.
Well, I mean,
Density itself, though.
well, you might not technically call it even, but you can see that it would balance you out.
Right, and that's why. So center of mass, this is one-dimensional. So we only have a single coordinate for center of mass, x bar, let's call it. Given by m sub y over m. M is just total mass. M sub y is called the y moment of inertia. Is it the y moment? Yeah, I think it is. Y moment's simple. Integral from a to b of x times rho of x dx. For derivation, watch the video. Total mass is also fairly simple. Oops. Just the integral of the density. Fucking mass first. Rho. Rho. It's a Greek letter. The Greek letter rho. Well, just a function, right? Rho means density. Well, it's just a function. So that's rho of x. Right, so it's just the function. Total mass. Integral over the interval, -3 to +3. Of the density. Is 1 + 3x squared. Integrate 1, that's just the length of the interval, which is 6. Antiderivative 3x squared is x cubed. From 3 to -3. Just twice of 3 cubed. 3 cubed is 27, twice that is 54. Total mass would be 60. And then whatever the units would happen to be. It depends on what the units of density is. Y moment, integral from -3 to +3 of x times your density. X squared over 2 from 3 to -3, that is 0. Three x to the 4th over 4 from 3 to -3 is also 0.
It's 0.
Yep. 3 squared
This applies.
Oh, wait, yeah. That's
minus -3 squared wind up being the same thing.
So this applies that this rod has the, this mass is constant, right? That- Something.
Well, mass is, well,
But then the-
ignoring relativistic effects, mass is always constant.
Okay.
Center of mass, Y moment over total mass, so just 0 to 60, which is 0. Looks about halfway. No, it doesn't. The halfway point would be here. Not good enough for government work. We're going to pretend that's the 0.0. Right, so put a fulcrum there. The wire would be perfectly balanced. We're again going to look at a linear wire. Interval will be 0 to 3. Density is now a piecewise function. Right, at least each piece is constant though, which makes life a bit easier.
Isn't this another one you could solve without integrals? You know, there has to be equal mass on both sides. You see the total mass adds up to like 13. Is it 13? Yeah,
Why does there have to be equal mass on both sides?
because that makes sense. Wait, never mind that.
The densities are different.
It's gonna-
If it was a single constant density, I'd agree. You'd have to have equal mass on both sides, but here the densities are different. You have 4 for the first 2 units, and then you have 5 for the last unit. So it doesn't necessarily mean the masses are going to be the same. And here they won't be. Total mass. Integral from 0 to 3 of your density. But density is piecewise. Which means this gets broken up into 2 integrals, right? Integral from 0 to 2. 4. Plus the integral from 2 to 3. A 5. And that's why I said at least each piece is constant, which makes it a bit easier. 4 times the length is 8. Plus 5 times the length is 5. We have a total mass of 13. Y moment. Integral from 0 to 3 of x times your density. All right, again, density is piecewise, so this is going to be split up. Two x squared from 0 to 2 is 8. We get 5/2 x squared from 2 to 3. Right, so x squared from 2 to 3 would be 9 minus 4 is 5. Times 5/2 is 25/2. Eight plus 25/2 would be 16 plus 25 all over 2. 41 over 2. Center of mass x bar would be 41/2 over 13. Be 41/26. Max is 15, right? So that's what, slightly over 1.5? So not quite the midpoint. Which if you look at, actually should be slightly less than 1.5. Right, 26 and oh, it is slightly over. You have to go into the 5 kilogram. That doesn't make sense.
But the things closer to the fulcrum essentially count less, so it makes sense you'd have to put the 5 way closer.
In this case, you'd want it where you have equal mass on both sides of the fulcrum to balance it. Right, think of a weight. You have to have equal mass on both scale. You have to have equal mass on both sides of the scale.
Well, sort of, but if you had like a fulcrum here, and if you had a bit here versus the same mass all the way out here, much farther, then it's gonna not balance.
Which doesn't make sense to me. The way I'm thinking of it. Oh, wait. Never mind. The 5 kilograms is from 2 to 3. It's not actually perfectly split. Okay, that does make sense now. I was thinking it was half of it was 8 and the other half was 5. That's not how this works. 2/3 of it is 8. 1/3 of it is 5. Okay, I'm back. Oh boy. Okay, why is this not working? Why did you just decide to stop working? Oh dear. Oh, what's going on? So if we're talking center of mass of a lamina, we typically refer to that as a centroid, but it's the same thing. To find the centroid of the region with density, with constant mass density rho enclosed by the parabolas y equals x squared minus 3 and y equals negative 2x squared. So total mass density times area. Since we're dealing with constant density, that makes this simple. And we know area of a region. Right? Remember we did that area between curves? So that's what we get for total mass. The y moment. Rho times the integral from a to b of x times the difference f of x minus g of x. Again, f of x greater than or equal to g of x on the interval. X moment. You have to rewrite each of your curves as functions of y. Oops, I forgot the y in there. Then it's the same. Right, so you're going to redefine your interval, C to D. Remember, that's an interval for y. And it's the integral from c to d of y times h of y minus k of y dy. That is a bit of a pain. You want to keep it as functions of x, then that is the same as rho over 2 times the integral from a to b, f squared minus g squared. Whatever you want to do, I don't care. The centroid or the center of mass? Right. The x coordinate is my over m. The y coordinate is mx over m. And by the way, it's only if density is constant. If density is variable, let's say density varies as a function of x, then that row of x would go in the integral for each one. We need an interval. How are we going to determine the interval? So x squared minus 3 equals negative 2x squared. Solve for x. It's not difficult to do, but I want Mathmata to warm up anyway because I'm going to be using it. You can go away. Cute. Get -1 and +1. Call this region. Lamina. Like that better. X from -1 to 1. And any text. Well, let's also turn the axes off. And plot labels, we'll use expressions. So that is our lamina. I have the labels up there purely for reference. Over that interval, negative 2x squared is our larger function. The total mass will be our density rho times the integral from -1 to 1. F of x, the larger function, minus g of x, our smaller function. Simplifies to what? Negative 3x squared plus 3, right? That'll be negative x cubed evaluated from -1 to 1. That's just what, 2? Plus 3 times 1. That's not right. Because it's 3 times 2. Length -1 to 1 is not 1, it's 2. We get a mass of 4 times rho. And y is easier. Rho times 0 from -1 to 1 of x times the f of x minus g of x. Which is 0. By symmetry. Here's the fun one. Mx rho times the integral from -1 to 1. Larger function squared minus smaller function squared. Oh, it's actually rho over 2. Always forget the half.
So when we're asked to give the center of a constant mass density like this, are we always gonna give it as a, or different, like, two different separate points?
If it's of a lamina, then yes, it needs to be an ordered pair. All right, so once you do algebra, simplify it. We should get rho over 2 times the integral from -1 to 1, 3x to the fourth plus 6x squared minus 9 dx. So 3/5 x to the fifth. 1 minus -1 is 2. So that's 6/5. Two x to the fourth. X to the fourth from 1 to -1 is also 2. So times 2. And minus 18. For 2. We're gonna have what? 26 over 5 minus 18. 18 times 5. 90. So 26 minus 90. Negative 64. Y moment be negative 32 rho over 5. Or x moment is negative 32 rho over 5. Eight fifths. There's a rho in both numerator and denominator, isn't there?
Swap the x and y. Like for the x, like my we solve for.
Yeah.
0, we got 0, 2, 0, there.
X bar is my over m. Right, because essentially what my is measuring is it's measuring distance from the y-axis times mass is really what it's doing. Well, distance from the y-axis is horizontal, right, which is an x. That's why that goes with x bar. It's called the y moment because it's measuring moment of inertia with respect to the y-axis. That was random.
I'm sorry, I just like saw how bright it was outside and I was like, oh my gosh, it's not dark.
I mean, if you want daylight, I can always just launch you to the sun. This brings a very important point up. Notice that rho doesn't play a role in the center of mass here. So if you're just asked for the centroid and it's constant density, you can just set rho to be 1. Keep in mind, if I'm also asking for mass, you can't do that. So center of mass is the 0.0 negative 8/5. Uh-oh. Why did that not work? Oh. Yeah. Oh, look, as expected, dead center. Right, because it's constant density, so you would expect it to be dead center. Yes, that means we did it right. Find centroid with constant mass density rho of the region bounded by the x-axis and the curve y equals cosine of x for negative pi over 2 less than or equal to x less than or equal to pi over 2. Negative pi over 2 to positive pi over 2. Is cosine above or below the x-axis? It's above. Constant mass density would just take rho to be 1. I'm actually going to call this m star. I'm just going to say it's reduced mass. Since we're just setting the density to be 1, doesn't matter. So we're going to integrate minus pi over 2 to pi over 2 of simply cosine of x. Antiderivative cosine, negative sine. Sine of pi over 2. Wait. I did the mistake. Derivative cosine is negative sine. Antiderivative is positive sine. Sine of pi over 2. Sine of negative pi over 2. Reduced mass is 2. Would be a problem if mass was 0. Oh joy. X times cosine x. That would be integration by parts.
Fortunately, this is one where it's symmetrical, so you don't have to do it.
True, it is symmetrical. I'm just going to use the formula to plug it in. It's cosine x. Cosine pi over 2 is 0. Cosine negative pi over 2 is 0. That's nice. Sine of pi over 2 is 1. So it's pi over 2. Sine of negative pi over 2 is negative 1 times negative pi over 2 is pi over 2. You get pi over 2 minus pi over 2 is 0. Yeah, did it again. 1/2. Integral from minus pi over 2 to pi over 2. Cosine squared. Using the reduction identity. Cosine squared. 1 plus cosine of 2x all over 2. Cosine of 2x is going to integrate out to 0. What is the period of cosine of 2x? It's pi. The interval on which we're integrating over. Isn't it one full period? If you integrate over any multiple of a period of a periodic function, it's automatically 0. That is a useful property. And one that I will be making use of quite often. Especially if you take Calc 3 with me. It's one I use very often in Calc 3. Oh, so we're just actually integrating 1. Which is just the length. Which is pi. We just said that. That integral is just pi over 4. So the center of mass is located at 0 pi over 8. X bar is the y moment divided by mass. No, it's pi over 4 because of the 1/4. The integral from minus pi over 2 to pi over 2 of 1 is just pi. No. It's pi over 4 because I'm multiplying by a 4th. But if you just integrate 1, it's pi. Maybe I should. Plot 0 as well. Just to close it off. Right, so again, as expected, right in the middle. Centroid of the region, constant mass density cut from the first quadrant by the circle of radius 3 centered at the origin. We're told constant mass density, so we can take rho to be 1. Circle of radius 3 centered at the origin. What is the equation for that?
Squared plus y squared equals 9.
Mass. Integrating from what to what? And what are we integrating? What's the integrand? Which is trig sub. Or you can use geometry. What is the area of a circle? So there'd be 9 pi, right? But we only have a quarter of the circle, don't we? So its area would be 9 pi over 4. That's what this integral is. You want to go ahead and use trig sub to evaluate this? Go ahead, I won't stop you. How'd we do this one? What would the technique be?
You have to use the trig sub,
I mean, you could use trig sub. There's an easier way.
Guessing it'd be a u sub.
This is just simple u sub. Derivative of 9 minus x squared is negative 2x. We have an x. Perfect. U to the 1/2. 2/3 u to the 3/2. Negative 1/3. Now 9 minus x squared to the 3/2 from 0 to 3. At 3, that's 0. At 0. It is 9 to the negative 9 to the 3 halves. Which is negative 27. You get 9.
For this one, since you know that like this area that we're finding the centroid of is going to be symmetrical over y equals x. You don't have to find the next one because it's going to be the same.
Use symmetry. Circle is symmetrical about y equals x. It's also symmetrical about y equals negative x. So this should be the same. Just going to verify it. In this scenario, it would not be advantageous to use that. We're going to set this up as an integral with respect to y. What would the bounds be for y? What is it? Also 0 to 3. What would our function be? Which is precisely the same. It's the exact same integral, just a different variable. Verification complete. Center of mass is then 9 over 9 pi over 4. Which is the 0.4 over pi, 4 over pi. Okay, this one is going to be a little bit trickier. I'm going to have to do this. So I can now just do this. Then I want x equals 0 and y equals 0 because we're in the first quadrant. Set here. That string to false. Oh, bugger. I forgot contour plot doesn't. Went the wrong bloody way. Negative to negative. There we go. So smack dab in the middle as expected. Questions on center of mass. Second test is now available. It'll be due before the start of next Tuesday's meeting. All right, same rules. Complete on loose leaf paper. Scan your test as a single PDF file. Screenshots can be separate. All right, allowed to use notes, textbook, course material, any model calculator, allowed to use Mathematica. Particularly for question 1, I am requiring screenshot of your Mathematica input and output. So you can just upload that as a separate JPEG file. Just make sure you label it question 1. Nothing else requires it. If you want to be safe, if you're going to be using technology to evaluate integrals, include screenshots of your calculator screen if you use a calculator, or the Mathematica. Again, just be sure that you label each question so that I know which question that screenshot goes to. Doing so at least lets me see if you input it correctly. You don't have to do that, but you might get partial credit if it's wrong because you input it wrong and I can see what you did. Again, 5 questions. Fairly straightforward. I don't think it took me too long to write up the solutions to this. So, not super difficult. Of course, as always, have fun. We get to start sequences on Thursday. Many consider this to be the toughest part of Calc 2. I don't. I think integration techniques is. However, series does require a different type of thinking. We're going to have a total of 7 tests, I believe, and then 3 special series, something like that. It's like 10 or 11 tests. Not like I'm giving you 11 tests. It's 11 tests for the series. So I'll give you a series and ask if it converges. You have to figure out which test to use to determine convergence or divergence. So it's not as straightforward as what we've been doing. This is going to require some critical thinking, some pattern recognition. In fact, this is what math is truly about, pattern recognition. None of this plug and chug crap that we've been doing. That's boring. That's not math. You're also not going to be able just to say, yes, it converges. You actually have to explain why it converges. So it's essentially a proof. Right? If you think it converges, you say converges, and then you have to prove it to me. If you think it diverges, you have to tell me it diverges, and then you have to prove it to me. A correct answer of convergence or divergence is only worth 1 out of 10. It's your work that I'm interested in. Can you use the test properly? Can you interpret the results properly? That's where the bulk of it's going to come in. And that's why many consider this to be the toughest. I'll say it again when we get there, but I would recommend as we start to cover the tests and the special types of series that you have a separate sheet of paper to write them down on, just so you have them handy. And don't have to flip through several pages to try and find the right one. We start our study of series by looking at sequences. Right? Because how do you sum up an infinite series? It's an infinite sum. How do you find a sum of an infinite number of terms? Well, it turns out it's the limit of the sequence of the partial sums. So we have to actually look at sequences first before we can fully appreciate infinite series. If you've taken discrete math, you should be familiar with sequences. You study them in discrete math. However, you don't consider, I think you like infinite sequences. You don't look at convergence of sequences, though, so that's going to be new. And you also don't look at infinite series, but you should be familiar with sums if you took discrete math. Calc 2 just extends that now to infinite. So it's going to be fun. We wind up concluding the unit by looking at power series. Every function has a series representation to it. That's what we end with. If you plan on taking differential equations, you will see power series again. If you don't, you'll never see them again. This is one of those weird topics in Calc 2 that you can probably just not cover and get away with it. It's kind of weird.